Good morning. So, we had discussed yesterday about explicit methods for wave equation, and then we started implicit method. So, let us continue with the details on implicit method and also stability aspects for both explicit and implicit methods. Okay. So, in order to derive implicit method for wave equation, so let us consider the explicit method. Okay. Consider the explicit method given by so this is the explicit method. Then replace RHS in RHS Uij by Uij minus 1 Uij plus 1. So, this is a special case as I mentioned. So, then if we do that, we get so that means we are expanding the scope of the levels. So, j to j minus 1 and j plus 1 plus u I plus 1 j minus 1. Then for this term then since this is at j minus 1 we keep it. Okay. Then after readjusting we get terms this j minus 1 j minus 1. So, this is a kind of a specific method. Okay. You can adjust. So, lot of terms get cancelled and then lambda square cut through across. So, hence lambda must be non-zeros. Okay. So, indeed lambda is non-zero. So, we get. However, one can derive more general implicit method. Okay. So, let us see that. So, in general, if one replaces Uij by in RHS of explicit method. Okay. So, if we consider the explicit method, so this is given by so this is so now each of them. So, let us call this A. So, for all these replace approximation of the type A. So, when I said of the type A, because this is for u I j, correspondingly we have to adjust for I minus 1 and I plus 1. Okay. So, if we do that, we get so different literature refers different notation. So, in this case theta is a kind of a weight, okay. So, which can vary, and of course, when we discuss the error, theta will also come into picture, and then when we discuss stability, theta will also come into picture. Okay. So, when we replace right hand side of explicit method by an approximation of this type, we get this, and we have to abbreviate what is these notations. So, this notation is, so this is with respect to x, which is nothing but the central, and this is t. Okay. So, that means this is clear when operates on u I j, exactly this appears, whereas here on u I j plus 1. So, index has to be adjusted, and this is exactly this, and here again index has to be adjusted. Okay. So, this is implicit method, general implicit method. Right. So, now let us try to fix theta for a special case. Okay. So, let us say when theta equals to half, we have u I j minus 1 which is nothing but, so this term is independent of theta. So, exactly I have written the same. Okay. Now, when theta is half, this term goes off and we get these two. Okay. So, let us simplify. So, this is equals to lambda square by 2, because theta is half. So, that comes out, then d 2 x operating on I minus 1 and I plus 1. Okay. So, this we get minus 2 I plus u I plus 1. Let me check one more time. So, this is on I j plus 1 and d 2 x. Therefore, I plus 1 j plus 1 I j plus 1 I minus 1 j plus 1. Okay. So, I minus 1 j plus 1 I j plus 1 I minus 1 j plus 1. Okay. So, here minus I used. So, this is plus. Then similarly, the next term, which one? Here I j minus 1 d 2 acting on it. Okay. So, this would be j minus 1 so this gets simplified. So, all higher time level to the left and lower to the right. So, we are just collecting, for example, u I minus 1 j plus 1 I minus 1 j plus 1, the coefficient is lambda square by 2 and no other place it appears. So, therefore, when it is left we have minus. Then u I j plus 1, we have 1 u I j plus 1 here, and we have minus lambda square. So, when it is to the left plus lambda square minus so this is also we have I plus 1 j plus 1 are the only term. So, minus to the left hand side. So, this is equals this we are pushing to the right hand side. Okay. Then I minus 1 j minus 1 with the lambda square by 2. Then I j minus 1, I j minus 1 we have this. So, lambda square by 2 then I j minus 1 then the remaining. So, this is a special case where theta is half. Suppose if you vary theta is 1 by 4, then we get more terms, because when theta is 1 by 4 this term survives. When theta is half, this term got vanished. Okay. So, correspondingly we get more terms, however, they get adjusted in terms of the coefficients. Okay. So, now this is for theta half, and let us say we consider this and try to solve a specific problem. Okay. So, example, solve subject to the initial conditions and boundary conditions. This equals to 0, say lambda is 3 by 2, h is 1 by 4. Accordingly, k is lambda h 3 by 8. So, h is 1 by 4, and let us say we are solving this. So, then we have so I 0 1 2 3 4. Okay. So, now consider our implicit equation. So, which is given by so this is our implicit equation when theta is half. Now, lambda square is 9 by 4. So, when it is lambda is 3 by 2, this gets simplified to okay, and then 1 plus lambda square. So, 13 by 2 So, this will be 1 plus lambda square, yeah. So, 13 by 4, 13 by 4 u I j plus 1 minus 9 by 8 I plus 1. So, this equals these terms 2 u I j plus 9 by 8 minus 13 by 4 u I j minus 1 plus 9 by 8 I plus 1 j minus 1. Okay. So, now please remember we did not write one more initial condition, we did not write one more initial condition. So, this initial condition would be on say equals to 0. Okay. So, now when we run this at j equals to 0, we get terms including minus 1. Okay. So, let us see what will happen. So, now I just keep it so that you can. So, this when j equals to 0, we get 1, then 13 by so this is so 13 by 4 u I 1 u I plus 1 1 equals 2 u I 0 plus 9 by 8 u I minus 1 minus 1 okay. So, these are the fictitious values. However, we have our initial condition. So, let us discretize that. So, this would give us u I 1 equals to u I minus 1. Okay. So, if we use this on the right hand side, we get, you see, u I minus 1 1, and we have already u I minus 1 1 with a minus 9 by 8, and then this goes. So, using B, we get these quantities will be doubled. Similarly, u I minus 1 is u I 1. So, plus 13 by 4. So, 2 times 13 by 4. So, all the terms on the left hand side gets doubled. So, we get minus 9 by 4 plus 13 by 2 minus 9 by 4 equals to just okay. So, this is for j equals to 0. So, now we get at each grid point at time level 1. Okay. So, we use this. So, therefore, at j equals to 0, we have okay. So, now we have to run at each grid point. So, this is nothing but 2 sin pi by 4, our initial condition pi x. So, 1 is, so this is due to x 1 is 1 by 4. Okay. So, then I is 2 then I is 3 . So, this can be put it in matrix form. So, you can simplify. So, this will be 1 by root 2 1. Okay. So, why how did we get here u 0 1? So, we have discretized the equations. Okay. So, this becomes 0, then 4 1. So, this becomes 0. So, therefore, in the first equation we have u 1 1 u 2 1. Okay. And the second equation we have 3, and third equation we have only u 2 1 and u 3 1. So, this implies we can solve u 1 1. Okay. So, this is explicit method. Implicit we get system of equations from the explicit method by considering a weighted approximation of all the values at jth time level. We spread over j minus 1 and j plus 1 and then obtain implicit method, and this is the solution for a specific case. Now, let us see the stability aspects of both explicit and implicit methods. Okay. Stability of explicit method. So, we consider so, this is our explicit method. Then let u I j. So, for convenience we are changing, right. So, this is Fourier stability analysis. Okay. Then when we substitute this in the above equation, we get so, this is because of j plus 1 we get zeta of q plus 1, okay. So on and so forth. Then we are left with one term here with the positive and then one term here with the negative. Okay. Then we have because of this. So, this further can be simplified. So, this is quadratic and the roots so these are the roots. Okay. So, now for stability we have to consider the stability conditions, roots must be within the unit circle. So, less than or equals to 1, okay. So, including the boundary. So, zeta 1 2 are given by okay. So, now if mod 1 minus 2 lambda square, if this is greater than 1, then is greater than 1. Okay. So, this is implies unstable. Okay. Then if this is less than 1, so let us write if is less than 1, then the roots are complex conjugates, a pair whose magnitude is 1. Then if equals to 1, then 1. So, therefore, yes, you are correct, method is stable for so this implies, so this is a stability criterion for explicit method. Okay. So, now let us see for the implicit method. Of course, these are Fourier series stability analysis. Consider okay. So, now if we do similar then substitute, we get equal to 0 where R is. So, this is just an algebra. So, I am not giving the details, you can work it out. Okay. Now, if mod r greater than 1, then we have zeta 1 greater than 1. Okay. So, the method is unstable. Then if mod r less than 1 less than or equals to 1, then the method is stable. So, you can compute the roots. So, from there I am concluding. So, therefore, mod 1 minus 2 lambda square so, this is less than or equals to 1. So, this implies minus 1 less than 1 minus 2 lambda square 4 theta lambda square less than 1, okay, because these are sin square beta h by 2 sin square beta h by 2. Okay. So, therefore, 1 plus 1 minus 4 theta. So, this means from here, see, this must be greater than or equal to 0. So, if we pick up theta greater than or equals to 1 over 4, so that this is stays positive. So, we get remark for theta greater than or equals to 1 4 unconditionally stable, okay, because of this, right. Then if theta is then stable for okay, we can obtain. So, this is the stability aspects of implicit method. So, the stability method we have discussed is based on von Neumann stability, that is the Fourier stability. So, let us see the matrix stability as well. Okay. So, this is of the implicit method. Okay. So, consider so, this is the case of theta equals to half. So, this will be so, I am expanding this operator. Then this one, okay. So, this on slight rearranging u I j plus 1 minus lambda square by 2 u I minus 1 j plus 1 u I j plus 1. So, all the quantities at j plus 1 are to the left. Okay. So, now if we introduce the error, that means if we denote E I j by u I j minus u bar I j. So, the exact equation satisfied by the difference equation minus the u I j numerical. So, that is the local truncation error. So, now with this notation, if we calculate, so then let us look at the coefficients u I j plus 1. So, we have 1 plus lambda square. Okay. So, let us do little finer. So, this will be 1 plus lambda square u I j plus 1 minus lambda square by 1 u I minus 1 j plus 1 minus u I plus 1 j plus 1. Okay. And right hand side 2 u I j, we have this term. So, minus 1 and minus lambda square. Okay. So, this will be minus u I j minus 1 plus lambda square by 2 So, if we introduce the error, then if you look at it I minus 1 j plus 1 here, right. So, then I. So, the coefficients are so in this form. Okay. This is the standard form we have. So, this is our matrix A. Okay. So, why this is? Because if j is 0, we have boundary points. Okay. So, with this notation, the equation star becomes A u j plus 1 2 u j bar So, what is the notation? We have this equation. So, this produces matrix A on j plus 1. So, we are using the notation u I j is u j. Okay. So, with this notation, this contributes to matrix A, okay, and the left hand side they are at j plus 1. Okay. So, now here similar matrix, however, on j minus 1. Okay. So, therefore, it reduces to A u j plus 1, then 2 u j, then the same coefficients with a negative sign. So, therefore, minus a u j and the boundary terms. So, this is what. Okay. So, now this suggests that E j plus 1 is 2 okay. How did we get that? So, you can write at other time level okay, and then take the difference. So, then we get a E j plus 1 okay. So, here we get a E j plus 1 is 2 E j minus a E j minus 1 and the error b j boundary points they get cancelled. So, from here we get this. Okay. So, this can be written as so, we have just adjusted, we have supplied one more equation. So, that we can put it in a matrix form. Okay. So, this implies so where okay. So, now in order to discuss the stability we have to discuss the eigenvalues of P. Okay. So, eigenvalues of P are so this implies so these are the eigenvalues. So, therefore, zeta is so this is just an algebra. Okay. So, which is greater than 1. So, eta k. So, therefore, mod zeta is 1 for all k, hence stable. Okay. So, this is stability of implicit method. Okay. So, we have seen both general case we have seen using von Neumann stability of the implicit method, and when theta equals to half we have seen the corresponding matrix stability. Okay. So, let us see couple of problems using these methods. Okay. So, consider okay. So, the problem is if the equation is approximated by by explicit finite difference scheme given by and the derivative is by a forward difference scheme estimate EI1, okay, estimate EI1. So, that is the error. So, I will briefly discuss how to approach this problem. Okay. So, we have E is this is the notation we are following, and consider H equals to k, that is delta equal to delta k. Okay. So, then we want to, so this is the explicit scheme and derivative to be approximated by forward. So, this implies by k equals to g I. However, this is true at t equals to 0, j equals to 0. So, this implies u I 1 minus u I 0 equals to k g I. So, this implies u I 1 equals to, so k equal to h. So, I am using h notation plus f I, okay, because u I 0 is so I have used, okay. Then expand Taylor series of this u I 1. So, from that u I 1 equals u I 0 okay. So, this 1 means j equals to 1. So, that is t j, okay. So, 1 means first increment. So, therefore, that is expanded with respect to t 0, okay. So, where this is error term, okay. So, from this and we have h g I plus f I. So, this implies is less than or equals to h square by 2 m 2, where m 2 is maximum of okay. So, this is the estimate. Further we can compute how the E I j. So, this is the estimate, okay. This solves the given question. However, in order to see the behavior of E I j as h goes to 0, what we do, we compute so E I j plus 1 is E I plus 1 j plus E I minus 1 j minus E I j minus 1 plus h 4 by 6 m 4 into constant, because what was the method approximation, you can see this. So, if we expand Taylor series and then try to obtain the equation satisfied by the error, we have E I j plus 1 equals E I plus 1 j plus E I minus 1 j minus E I j minus 1. So, that is what I have written E I plus 1 j, E I minus 1 j minus E I j minus 1, and this is the error term. So, where M 4 is max of T 4, okay, and C is a constant less than 1, right. So, when j is 1, E I 2 is plus call this some T, okay. So, however, using the estimate so this can be made. So, this is one term from here and similar estimate from here, and this is 0 because at t equal to 0, j equal to 0. So, we get 2 times h square by 2. So, this is a rough idea. Similarly, if we proceed okay. So, for each, so you can make it bounded by, so from here to so we may get 4, okay. Then similarly for the remaining terms, okay. So, one can generalize j plus 1 h square by 2 m 2, and for t repeatedly for each one 2, okay. So, it will be magnified of this order. So, same process if we follow, we can get this, okay. So, therefore, mod E I j equal is less than equals to j h square by 2 m 2, because when we are replacing j by j minus 1 plus okay. So, this can be because we have j h equals to t, okay. So, I have used that. So, this goes to 0 as h goes to 0, Okay. So, this is a simple example where the error has been iteratively used, and then the estimate at first time level that we have computed has been used iteratively, and then we have shown that the error is bounded. Okay. So, this gives us idea of both explicit and implicit methods for hyperbolic second order. Okay. So, now there is a special feature of hyperbolic PDEs. This is using finite differences. However, there is other concepts called method of characteristics, and using numerical methods one can compute solution of hyperbolic PDEs. So, in the next lecture we discuss on method of characteristics. Until then, bye.